Hello, welcome to Hawk Math. Today we're going to be doing the MIT Integration B qualifying exam from 2019. Now in this exam, participants are supposed to have 20 minutes to compute the following 20 indefinite and definite integrals. But in this video, I'm not going to be taking this in a time limit. I'm just going to be going through the integrals in a quick way to show how to solve this certain test, but I'm also going to be thoroughly explaining how to complete every integral. So I really hope you enjoy. Let's get started. So starting with question 1, we see that we have the tangent of cosine of x. And if you look at the bounds, it's from 0 to 2 pi, and we know that cosine of x on the integral is periodicity of 2 pi, and tangent is period of pi. So if we think about it, cosine looks like this. And so on the interval from 0 to 2 pi, its area is just 0. So when we take this tangent, which also is a period of pi, of cosine on this interval, it's also just going to be 0. So we can just say 0 for this and we're done. Moving on to question 2, I notice a property that when we take the derivative of x plus natural log of x, we get 1 plus 1 over x, which looks something similar to this. So I'm going to see what happens if we were to take the derivative of ln of x plus ln x. Well, taking the derivative of that, we get x plus ln x, and on the numerator is multiply the derivative, so 1 plus 1 over x. But we can multiply the numerator by x and the denominator by x, and this cancels out, just giving us an x plus 1. And there we go. That is our original integral. So this is just the antiderivative of what we have. So we're done. I'm not going to be writing the plus c for the rest of the test because you don't need to for the MIT Integration B. So looking at question 3, I see that maybe we can split up this addition in the exponent. So we have e to the x times e to the x plus e to the x e to the negative e to the x. And this, I see this is pretty easy to integrate because this is the derivative of the exponent. So this first part just becomes e to the x. And similarly, this second part is going to be a minus e to the negative e to the x. Because if we were to take the derivative of this, we'd get e to the negative e to the x times, for chain rule, negative e to the x, which will cancel out, making us a plus, giving us this e to the x in front. So it's just that. Okay, moving on to question 4. Well, I noticed that the denominator factors, and we could probably do partial fraction. So we have a over 1 minus x plus b over 1 plus x equals 1 over 1 minus x squared. So we have a plus b equals 1, and then we also have a minus b equals 0. So 2a equals 1, a is 1/2, and then b is negative 1/2. So we have 1/2 natural log of 1 minus x over 1 plus x is the antiderivative. Now we need to evaluate this from negative 1/2 to positive 1/2. But before I do that, I'm actually going to note that this is an even function. So I can really just write this as 2 times that from 0 to 1/2. So 2 times the 1/2 cancels out in front, just giving us that. And now this is a little bit easier to plug in. So you have plugging in 1/2, we get ln of, well, 1 minus 1/2 is 1/2 over 3/2 is 1/3. Then minus ln, when we plug in 0, we get 1 over 1, which is just 1. So this gives us ln of 1/3. Now, I believe I made a mistake somewhere in here because if we look at this function, it's always positive on this interval, and ln of 1/3 is equal to negative ln 3, which is a negative number. So because it's positive, I'm going to look for where I missed a negative sign, and I will cut back to you. Okay, I found my mistake. I went too quickly, and b should be positive 1/2, which would make this expression become the natural log. So if I was writing it out completely, we have 1/2 over 1 minus x plus 1/2 over 1 plus x. Now, integrating this, we're going to get 1/2 times the natural log of 1 plus x, and then I missed this negative when we integrate this on the denominator. So this really should just be flipped on the inside. So this should be 1 plus x over 1 minus x. Sorry about that. So in the end, we're just going to be left with natural log of 3 as our answer. Okay, moving on to question 5. Well, this is 2 to the natural log of x, and there's a property that says a to the power log base b of c equals c to the power log base b of a. And if you want to prove this, you can take the log on both sides and simplify it out. So in order to continue, I'm just going to rewrite this expression as the integral from 0 to 2 of x to the power ln2 dx. And now this becomes a simple power rule. So we have x to the ln2 plus 1 over ln2 plus 1 evaluated from 0 to 2. Well, plugging in 2, we'll just plug in 2, and then when we plug in 0, we'll get 0. So this just becomes 2 to the power ln2 plus 1 over ln2 plus 1, and we're done. So for question 6, I'm just going to try to expand this and see what happens. I'm not really sure if this will simplify or not, but let's try it. So you have negative cosine 3x sine of 2019x, and then we have plus cosine squared of 3x, and then we have a minus sine of 2x times sine of 2019x, and then we have a plus sine 2x cosine 3x. Okay, from here, I think I'm going to try to use the formulas that are sine of A times sine of B or cosine of A times cosine of B and work the rest of this out. So I know that I'm just going to write these out for you. We have cosine of A times the cosine of B is equal to cosine of A plus B plus the cosine of A minus B all over 2. And similarly, sine of A times sine of B is equal to cosine of A minus B minus cosine of A plus B over 2. These are some basic trig identities that you can look up or derive on your own. And then for the third one, we're going to use sine A times cosine B is going to be equal to sine of A plus B plus sine of A minus B all over 2. Okay, so now using these identities, I believe we can simplify this down. So we're going to we have a cosine and a sine here, so this is going to be use of the third identity. So we have sine of A plus B, so 3x plus 2019 is 2022, so that's going to be sine of 2022. And then don't forget this negative in front, so I'm going to have a negative 1/2 times this sine of 2022x. And then we have a plus sine of A minus B, so plus sine of, that's going to become 2016x. Okay, sorry, I missed a parenthesis. Now moving on to this, this cosine squared through 3x, I'm going to come back to later, because that's just, we're going to have to use the double angle for cosine to simplify that down. Now we have two sines, so this is going to become, we're going to be using this formula right here. So we're going to have a negative 1/2 in front of again, so I'm going to write negative 1/2 times. Now we have cosine of A minus B. So cosine of 2 minus 2019 is just going to be cosine of 2017. And then we have minus cosine of A plus B, which is going to be cosine of 2021. Okay, now moving on to this last part, we have a sine and cosine again. So it's just going to be this third part. And this is going to give us, we have another 1/2, so we're going to have a plus 1/2 times sine of A plus B is going to be sine of 5x. And now we have a plus sine of A minus B, so that's going to become sine of negative x. And sine of negative is equal to negative sine x. And then we have over 2, which we already wrote out here. Now that we have this, we can finally integrate. Now, it's not going to be too easy to integrate, but if you notice our bounds from negative 2 pi to pi, that might allow for some nice cancellations if the periodicity happens to make the bounds cancel out. So the periodicity here is going to become pi over 1,011. So this will go to 0 because that goes into 4 pi evenly. Periodicity here is going to be pi over 1,008, so this will also go away. Now, cosine squared of 3x, we're going to have to come back to that later. Now, looking at these for the same reason of these, oh, sorry, I missed an x here and an x here. For the same reason as this, these are both going to go to 0 because of the periodicities, and same with these. So we're just left with cosine squared of 3x. So to integrate cosine squared of 3x, we're going to need to use the identity that cosine of 2x is equal to 2 cosine squared of x minus 1. So solving for cosine squared of x, we get cosine squared of x is equal to 1 plus cosine 2x all over 2. Now we can just plug in 3x into both sides. So this is going to be cosine squared of 3x is equal to 1 plus cosine of 6x over 2. So now we just have the integral from negative 2 pi to 2 pi of 1/2 plus cosine of 6x over 2. Now, for the periodicity reasons, this is going to be 0 again, so we should have 4 pi times 1/2, which equals 2 pi. Now, I'm sure for this problem, there's a much easier way to do it by noticing that everything cancels out from this first step up here, except for the cosine squared. And if you notice that, then you can solve this problem much quicker. Moving on to question 7, I immediately notice that this is the derivative of the innermost term, and this is the derivative of this if this was a sine. So I realized that if we were to do a u substitution, u equals sine of x, then this problem would just become the integral of sine of u. So, integral of cosine of u. So I believe this is just going to become sine of x plus c. So if we were to check, if we take the derivative of this, we get a cosine out in front, then we get a cosine of sine right there, and then cosine of sine of sine. So this is our antiderivative. Okay, moving on to question 8. I'm immediately reminded of the Gaussian integral, but the only problem is this t is on the denominator, so I'm going to try to simplify this by setting a u equals to 1 over t. And actually, I'm going to make this, to get rid of this right here, I'm going to make this a u equals root 2019 over 2t. So that way u squared equals this whole thing right here. So now du is going to become t to the negative first, negative root 2019 over 2t squared. Okay, so now rewriting this integral, we have the integral from, well, plugging in 0 into this is going to give us a positive infinity, and plugging in infinity is going to give us 0. So you have the balance from infinity to 0 of e to the negative u squared. And then right here we have du, I missed a dt, is equal to this dt. So we could rewrite this as negative 2 over root 2019 du equals 1 over t squared dt. So this 1 over t squared dt is nicely replaced with negative 2 over root 2019 times du. I'm going to use this negative sign now to interchange the bounds on the integral from 0 to positive infinity. Now we have the Gaussian integral, which I discussed in the previous MIT Integration Bee exam that I might do a video on in the future, but this part right here is famously known to be as root pi over 2. So you have 2 over root 2019 times root pi over 2. The 2's cancel, just giving us a square root of pi over 2019. And we're done. Okay, moving on to question 9. We see that we have sine of root x. Now this is a common problem. I have seen this before. It just takes a simple u substitution of u equals root x. So then du equals 1 over 2 root x dx, or 2 root x du equals dx. But root x is just u, so 2u du equals dx. Now we can just plug this back into here. We have the integral of sine of u, and then dx is 2u du. So we should have now a simple integration by parts problem. So we can differentiate u and integrate sine u to get 1, 0. Integrating sine u, we get negative cosine u, and then negative sine u. So our integral is going to be negative u cosine u. Remember, this whole thing times 2, so negative 2u cosine u. And then we have a plus sine u, so plus 2 sine u. And we are done. Now I forgot, I have to plug back in our u equals root x. So we have negative 2 root x cosine of root x plus 2 sine root x. So this wasn't that bad once you knew that u substitution, u equals root x, which should be one of the first things you should try if you don't know how to do this. Okay, moving on to question 10. I see another problem that I think might be work out similar if I try this u equals root x again. So let's look at that and see what happens. So by the same steps, we get 2u du equals dx. So we have the integral from 0 to 1 of u over 1 plus u squared. And now we have times 2u du. Well, this is equal to 2 times the integral from 0 to 1 of u squared over 1 plus u squared du. Now this integral is pretty easy because we can add 1 and subtract 1 from the numerator. So we have 2 times the integral from 0 to 1 of 1 plus u squared over 1 plus u squared minus 1 over 1 plus u squared. And you see how if we were to combine these fractions, they'd cancel out, giving us our original integral. So this is easy to integrate because this cancels out, giving us 1, and this is just arctangent. So we have 2 times x minus 2 arctan of x evaluated from 0 to 1. Well, at 1, we get 2 minus 2 times pi over 4. And then at 0, these both become 0. So rewriting this, we get 2 minus pi over 2. Okay, moving on to the second page. We have 11, we have a product of multiple cosine functions. Now, using trigonomic identities, we can actually combine these together. So some identities that we might want to use are the ones I wrote on the previous page, such that this cosine A cosine B equals cosine of A plus B times plus cosine of A minus B over 2. So using that, I'll keep that up here. Using that, we can write this as integral from 0 to 2 pi of, well, we have cosine of x plus times cosine of 2x is going to be cosine of 3x. And then we have a plus cosine of negative x, which is going to be the same thing as positive x. So plus cosine of x all over 2. Then we have that times cosine 3x dx. I'm going to move this 1/2 to the front of the integral now so that we can move on. Okay, so I'm going to distribute this 3x to both terms. So you have 1/2 times the integral from 0 to 1 of cosine 3x squared, cosine squared 3x dx, plus integral from 0 to 1 of cosine of x times cosine of 3x. Now using that same identity, that is going to be cosine of 4x plus cosine of 2x over 2. I'm going to write that over 2 in front again. So now we have this. Well, this isn't that difficult now because, oh, I'm sorry, I messed up the bounds for the whole problem. These should be 2 pi. So 2 pi and 2 pi. And just like in question number 6, this whole integral is just going to evaluate to 0 because our periodicity from 0 to 2 pi of these cosines is just going to repeat on that bound. So we don't even need to calculate that. It's just going to be 0. And we actually have the same exact thing as we had in this previous problem. We have the integral of cosine squared of 3x, which we had right here. Just making sure the bounds are the same. They are not quite the same. This was from negative 2 pi to positive 2 pi, but it's really similar. So we have 1/2 times the integral from 0 to 2 pi of 1/2 plus cosine of 6x over 2, as we found right here, dx. So rewriting this, this is going to be 0. And this is just going to become pi. So we have 1/2 times pi, which is equal to pi over 2. And we are done with question 11. Moving on to question 12, we see that we have what looks like the Gaussian integral, except there's an n in the exponent of x squared. And we're taking the limit as n goes to infinity. Now, there isn't really an easy way to integrate this at first sight. So we'll try to think of if we can do it a different way. Maybe series expansion would work, but if you try that out by taking e to the x and using its summation formula, it doesn't actually working out to give us a nice form. So let's try it a different way. Well, what does this function look like? Well, if we graph it, we see that first of all, it's always positive. And now what happens if x is greater than 1? Well, if x is greater than 1, we have e to the power negative x to the 2n. Well, as n goes to infinity, and if x is greater than 1, this part is going to be really, really large. And e to a really large number is going to be 0. So anything past 1 is going to be asymptotically close to 0. And because the limit as n goes to infinity, it basically will become 0. So this is at 1 right here. And by the same exact reasoning, from negative 1 and down to the negative side, it's also going to be at 0. Now what happens between negative 1 and 1? Well, this part is going to become less than 1 to the infinitieth power, which is 0. And e to the 0th power is 1. So this is going to become 1 from negative 1 to 1. So all we're doing now is integrating this from negative infinity to a positive infinity. So it's 0 a whole way, except for right here, we have an area of 2. 1 here and 1 here. So this integral is just simply equal to 2 by graphing. Moving on to question 13, I see that this expression might be able to be simplified if we were to take the natural log of it. So we could equivalently write this as e to the natural log of x to the power 1 over ln x. And then we can use the exponent property to bring this to the front. So this is equal to e to the 1 over ln x times ln x. Look at that, these cancel. So this becomes the integral from 0 to e of e, which is equal to e squared. Moving on to question 14, moving on to question 14, my first site is a whole bunch of more trig expressions. And so I think of maybe using trig formulas to simplify these into a nicer form. Well, I know that the trig identity for sine of x plus cosine of x, it's similar to this, but not quite the same. So we have sine of x plus sine of y is going to be equal to 2 times sine of x plus y over 2 times the cosine of x minus y over 2. Now we also have that cosine of x plus cosine of y is equal to 2 cosine of x plus y over 2 times cosine of x minus y over 2. Okay, now we can plug in our integrals. We have the integral from 0 to pi over 100. Okay, this first part is going to become 2 times the sine of the average of these, so 2 sine of 20 plus 19 is going to become 39. Sorry, 20 plus 19 is 39 over 2 times x, and then we have the cosine of this minus this is just going to become x over 2. So we have cosine of x over 2. Then our denominator will become 2 times the cosine of, we have the same thing, x plus y over 2, which is going to be 39, sorry, it's, 39 over 2, x, and then we have the cosine of x minus y, which is going to be cosine of x over 2 again, dx. Now if we notice, these will cancel out, and the 2's cancel out, and we're just left with the integral from 0 to 100, sorry, pi over 100, of tangent of 39 over 2x dx. Well, the integral of tangent is just the negative natural log of cosine of x, but then x here is 39 over 2. But then by chain rule, we have to multiply this by 2 over 39. So you have negative 2 over 39. So if you see, if we were to take the derivative of this, by chain rule, the 39 over 2 cancels out in the front. And we are left with evaluating this, sorry, this should be x, evaluating this from 0 to pi over 100. Well, at 0, we have cosine of 0, which is 1. And natural log of 1 gives us 0. So this goes away. Now what we do is plug in pi over 100 to get negative 2 over 39. Natural log of cosine of 39 over 2 times pi over 100 is going to become 39 pi over 200. And we're done. Moving on to question 15, I immediately see that we can factor out an e to the x from all these terms, and then we can use some trig expressions to simplify down what this says, just like in previous problems. So we have e to the x times, we have cosine squared minus sine squared, which is equal to cosine of 2x. Then we also have cosine x times sine of x, which is equal to 1/2 sine of 2x. So if we were to expand this e to the x, both of these terms just become a simple integration by parts problem. So let's write that out. We have cosine of 2x, and we're going to integrate e to the x. And then differentiating cosine 2x, we have negative 2 sine 2x, and then negative 4 cosine 2x. So this integral will become e to the x cosine 2x plus 2 e to the x sine of 2x, and then minus 4 times that integral again. Adding this to both sides, we see that 5 times the integral of e to the x cosine 2x is equal to this. So dividing by 5, we get the integral of e to the x cosine 2x is this. I might do a video in the future showing more in depth on why this works, but for now I'm just going to leave it like this. Okay, moving on to the second half, we are going to differentiate 1/2 sine 2x and integrate e to the x again. Okay, differentiating, we get cosine of 2x and then negative 2 sine 2x. So we get 1/2 e to the x sine 2x minus e to the x cosine 2x. And now we have minus 2 e to the x sine 2x. Adding this to both sides, we're going to get 1/2 plus 2 times the original integral, which is going to be 5/2 times the original integral. So now we need to multiply this whole thing by 2/5 to get the value of this integral. And then we're adding these together, remember? So this is our integral. But now we just need to rewrite this in one expression. So we have e to the x cosine 2x plus 2 e to the x sine 2x. Okay, now this part, the 2's cancel out, leaving us with a plus e to the x sine 2x over 5. I'm going to combine the fractions. And then here we have a minus 2 e to the x cosine 2x all over 5. Okay, now we can combine like terms. So we see that we have a e to the x cosine 2x minus 2 e to the x cosine 2x is going to become negative e to the x cosine 2x. And this part right here is going to become plus 3 e to the x sine 2x over 5. Moving on to question 16. I see that we have a sine of x over sine of x plus pi over 4. My immediate thought is to expand the sine of x plus pi over 4 on the denominator using the trig identity, but that won't help us because then we'll get multiple expressions on the denominator. But if we had those multiple expressions on the numerator, we could separate out the fraction. So in order to do that, maybe we can employ a u sub, u equals x plus pi over 4. This will now become the integral from pi over 4 to 3 pi over 4 of sine of, this will become u minus pi over 4, all over sine of u, yep, and then du is just dx. Now, expanding out this numerator, we can rewrite this as the integral from pi over 4 to 3 pi over 4 of sine of u times the cosine of negative pi over 4, which is just going to be root 2 over 2. And then we have a minus cosine of u times the sine of pi over 4, which is going to be root 2 over 2, all over sine u. And as I previously mentioned, the sine cancels out on the first term, and this will become a cotangent on the second term. So we now have the integral of root 2 over 2 for the first part, which is just going to be 3 pi over 4 minus pi over 4, which is 2 pi over 4 or pi over 2, times this. So pi over 2 times root 2 over 2. And then we have minus the integral of cotangent is just going to become natural log of cosine of u, evaluated from, times root 2 over 2 from this constant right here, evaluated from pi over 4 to 3 pi over 4. Okay, plugging in 3 pi over 4 into this cosine, we're going to get natural log of root 2 over 2. I will write this out. So we have pi root 2 over 4 minus root 2 over 2 times, well, natural log of cosine of 3 pi over 4. Cosine of 3 pi over 4 is going to be negative root 2 over 2. And then cosine of pi over 4 is going to become positive root 2 over 2. And if you notice, when you write those out, those terms will actually cancel out, and this whole thing will just become 0. So we're left with just pi root 2 over 4. Moving on to question 18. What I immediately notice is that I know the derivative of x to the x is equal to x to the x times ln x plus 1, and that reminds me very closely of what we have here. So, the derivative of this. Now, what I'm thinking is that maybe the derivative of this happens to give us something in the parentheses, or maybe if we were to remove this plus 1 and add another x out in front, the derivative of this part will leave us x times all that. So I'm going to try the second option. Let's take the derivative of x to the power x squared and see what happens. Let's set that equal to y. So take the natural log of both sides, x squared ln x equals ln y. So y prime over y, taking the derivative, equals 2x ln x plus x. And we notice that is precisely, now multiplying both sides by y, we get x to the x squared. And this happens to precisely be what we have in our integrand. So we know that this was the antiderivative of our expression. Now we just need to evaluate x to the x squared from 0 to 2. Well, at 2, we have 2 to the power 4, which is 16. And then we have minus 0 to the 0th power. If you take the limit of that from the right-hand side, you actually get 1. So this whole thing is equal to 15. This looks like a job for a partial fraction because we can factor this denominator. So we have a over x plus b over x plus 1 plus cx plus d over x squared minus x plus 1. Now this doesn't look too fun, but let's work through it and see what we get. So we have a times x cubed plus 1, so a x cubed plus a. Now we have a b times x times that, so plus bx cubed minus bx squared plus bx. Now for the cx plus d, we have a plus cx plus d times, we have x squared plus x. Now, expanding this out, we get cx cubed plus cx squared plus dx squared plus dx. Now, using partial fraction, we can write the coefficient of all the x cubes being equal. So we have a plus b, and now we have plus c right here, and that whole thing must equal 2. Now, looking at the coefficient of x squared, we have negative b, we have a positive c and a positive d. So you have c plus d minus b must equal 0. Looking at the coefficient of x now, we see that we have a b and a d. So we have a b plus d must equal 0. Now looking at the constant, we have an a, and we have just an a. So that means a equals negative 1. Well, if a is -1, then this first equation will become b plus c equals 3. Well, now we need to solve this system of equations, and we can do that by negating this and adding it to that. So we get c minus 2b equals 0. And then if we take this and if we take this equation and subtract that equation, you will get that 3b equals 3, or b equals 1. So if b equals 1, then c equals 2. And if if b equals 1, then d equals -1. Finally, we're ready to rewrite our integral. So we have the integral of -1 over x. Now we have b is 1, so we have plus 1 over x plus 1. C is 2, so we have plus 2x plus d, which is -1, so 2x minus 1, over x squared minus x plus 1 dx. Now, this actually becomes really easy to integrate because this is just negative natural log of x. This is natural log of x plus 1. And since this is the numerator is the derivative of the denominator here, this third part just becomes the natural log of x squared minus x plus 1. And if you wanted to combine these together, you could, but I'm just going to leave it like this for the answer. Okay, moving on to question 20, we have the cosine of arctangent of x. Now, whenever you have some trig function of some arc trig function, or inverse trig function, you can simplify that by using a right triangle. So if we have arctangent of x equals u, then tangent of u equals x. So drawing in a right triangle, if tangent of angle u is equal to x, then this hypotenuse must be x squared plus 1. So the cosine of u, which is what we want, is equal to 1 over root x squared plus 1. So this is really just the integral of 1 over root x squared plus 1 dx. Now, if you know your hyperbolic trig, you know this is simply just the inverse hyperbolic sine. So sine arc SINH of x. And you can stop there and be done. If you wanted to rewrite this in terms of its log form, you can. But I'm just going to write it like this because it's an acceptable form and be done with it. I may do a video in the future on how these identities and how to derive them. But for now, I'm just going to stick with this. So going back through my answers, I actually noticed I made a mistake on 15. It started way back here. I could have factored out this 1/2 from this integral. Then I calculated the integral of e to the x sine of 2x using integration by parts on its own. So in this integration by parts, I just took, I only used sine of 2x. Now down here, that would remove this 1/2 from the inside and this 2 right here. And this would add a factor 2 right here. And then I have this 1/2 on the outside. And now solving this integral, which is where I messed up before, this should really be 1/5 of that. And rewriting this out, we get that 1/2 times 2 should be a minus 1 e to the x cosine 2x. And then right here we have plus 1/2 e to the x sine 2x. So I forgot to multiply this whole term by 1/2 before. So this cancels out now with this term. And this leaves us, taking the sum of these two, leaves us with 5/2 e to the x times sine 2x over 5, which is 1/2 e to the x sine 2x. Which, expanding out the sine 2x, is e to the x times sine x times cosine x, which is the correct answer. So this is incorrect. So I really hope you enjoyed this MIT integration bee. I found it really fun. Please like the video and subscribe if you want to see more like this.